The College of Engineering and Agro-Industrial Technology, or CEAT, of the University of the Philippines Los Baños offers 5 undergraduate degree programs: BS Agricultural and Biosystems Engineering, BS Chemical Engineering, BS Civil Engineering, BS Electrical Engineering, BS Industrial Engineering, and 4 graduate programs: MS in Agricultural Engineering, MS in Agro-Meteorology, MS in Chemical Engineering, and PhD in Agricultural Engineering. It also offers research and extension services through the Agricultural Machinery Testing and Evaluation Center and the Center for Agri-Fisheries and Biosystems Mechanization. Since its institution, CEAT has envisioned itself to be a premier institute of higher learning in engineering education. A center of excellence in engineering instruction, research, and extension. A leader in the generation and promotion of applied technologies. And a partner of the government, industries, and international agencies for agro-industrial development. CEAT conducts agricultural training courses and seminars to our farmers through its research and extension units. It aims to upgrade and continually improve and develop its programs to become one of the best engineering colleges in the country. That will produce quality graduates who will generate innovational technologies that will serve the Filipino people. For years, CEAT has been recognized as top-performing school in various engineering licensure examinations, awarded by the Commission on Higher Education as a Center of Excellence and Center of Development, an AUN QA certified, and a National Center for Agricultural Research, Development, and Extension. CEAT is part of the Engineering Research and Development for Technology program of the Department of Science and Technology, a consortium of 8 universities offering mature engineering graduate programs. The program aims to address the lack of highly trained researchers, scientists, and engineers, and research and development engineering activities in the country. The college actively participates in different social events in the university to strengthen unity, cooperation, and smooth relationships between students, faculty, and staff. In the years to come, CEAT will continue to take greater leaps to achieve continuous honor and excellence. The College of Engineering and Agro-Industrial Technology, or CEAT, of the University of the Philippines Los Baños offers 5 undergraduate degree programs: BS Agricultural and Biosystems Engineering, BS Chemical Engineering, BS Civil Engineering, BS Electrical Engineering, BS Industrial Engineering, and 4 graduate programs: MS in Agricultural Engineering, MS in Agro-Meteorology, MS in Chemical Engineering, and PhD in Agricultural Engineering. It also offers research and extension services through the Agricultural Machinery Testing and Evaluation Center and the Center for Agri-Fisheries and Biosystems Mechanization. Since its institution, CEAT has envisioned itself to be a premier institute of higher learning in engineering education. A center of excellence in engineering instruction, research, and extension. A leader in the generation and promotion of applied technologies. And a partner of the government, industries, and international agencies for agro-industrial development. CEAT conducts agricultural training courses and seminars to our farmers through its research and extension units. It aims to upgrade and continually improve and develop its programs to become one of the best engineering colleges in the country. That will produce quality graduates who will generate innovational technologies that will serve the Filipino people. For years, CEAT has been recognized as top-performing school in various engineering licensure examinations, awarded by the Commission on Higher Education as a Center of Excellence and Center of Development, an AUN-QA certified, and a National Center for Agricultural Research, Development, and Extension. CEAT is part of the Engineering Research and Development for Technology program of the Department of Science and Technology, a consortium of 8 universities offering mature engineering graduate programs. The program aims to address the lack of highly trained researchers, scientists, and engineers, and research and development engineering activities in the country. The college actively participates in different social events in the university to strengthen unity, cooperation, and smooth relationships between students, faculty, and staff. In the years to come, CEAT will continue to take greater leaps to achieve continuous honor and excellence.
Hello, good morning, everyone. Let me just share my screen.
It means you can't stop.
Hello, good morning, everyone. Welcome to the celebration of the 109th CEAT founding anniversary with the theme Future Proofing Communities Through Engineering Innovations. And as part of this celebration, we have this webinar series which started last Monday. And we are now in the fourth day of our CEAT webinar series. And our webinar for today is hosted by two departments. We have the Department of Engineering Science and, of course, the Department of Civil Engineering. Therefore, it will be a fruitful and gracious day for all of us as we will be hearing two researches from the two departments. And thank you also for attending, even though it's a holiday today, but really a blessed day to be part of our CEAT anniversary celebration and be filled with ideas and insights from the engineering innovations from CEAT through the Department of Engineering Science and Civil Engineering. And by the way, I am Assistant Professor Claire Garing from the Department of Engineering Science, and I will be your moderator for today. And to formally start this webinar, let's have the opening remarks from the chairs of the two host departments. For the first opening remarks, let me present to you the recorded message of Assistant Professor Paul Michael Tornate, the chair of the Department of Engineering Science.
The Department of Engineering Science is the multidisciplinary service department at the College of Engineering and Agro-Industrial Technology. It was established in 1983 when CEAT was elevated into a full-fledged college from the former Institute of Agricultural Engineering and Technology of the then College of Agriculture. The department was conceived primarily to handle basic engineering courses and to serve as a springboard from which additional departments could evolve. At present, we still offer the basic ENSci courses for all the degree programs of CEAT. In spite of a relatively high teaching load, some of our faculty members delve into research in their fields of expertise.
Thank you so much, Sir Paul, for that opening message introducing the history and the efforts of the Department of Engineering Science. And now, let me call on the chair of the Department of Civil Engineering, Dr. Richelle G. Zafra.
Good morning, everyone, and welcome to the CEAT webinar series highlighting the research conducted by the different units of the college. From the Department of Civil Engineering, you will be hearing about our research on constructed wetlands, or COWET, as a nature-based solution to water scarcity. This research study was one of the top finalists in the 2020 Oscar M. Lopez Center's Climate Resilience Challenge. So please stay tuned to know the details of this very useful research. Thank you very much, Ma'am Claire.
Thank you so much, Dr. Zafra, for your welcoming and inspiring opening remarks for all of us. And now, let's move on to the presentation of the researches from the two departments. First is from the Department of Engineering Science. Just to share, through the years, the Department of Engineering Science, or we call it DES, its engagement in research has gradually gained numbers. Being a non-degree granting unit has not kept the department from taking on the challenges of basic and applied research. There have been several project involvements in material science related areas, such as nanomaterials, biopolymers, and metal property involvements. And to present the completed researches of our department and his DOST Preferred project, polyhydroxyalkanoate production from agricultural residues, we have UP scientist from the Department of Engineering Science, Dr. JRS Ventura.
Okay. So, kita po ba natin? Hello?
Yes, sir.
Okay. Okay, so good morning po ulit sa atin lahat, and I think mapayapang araw po sa atin. So I will be presenting some of the researchers of the Department of the Engineering Science, and likewise introduce also one of the big research that we have been under the DOST Assured grant. Okay, so the content of my presentation are the following. So I'll be dealing about the basic research that we have done before, and DOST funded projects, some ongoing projects, future research projects, and of later on introduce to you our laboratories. Okay, so these are just some of the basic research that we have so far. So we have bioadhesive production from microalgal biomass, and likewise we have researches on nanocrystalline cellulose or heavy metal removal in wastewater. We have metal research under the leadership of Professor Assistant Professor Mudimbayan, and likewise we have some research on ceramic materials by the group of Engineer Balsa. Okay, for the overview of the bioadhesive production is that this is a complement of the microalgal biodiesel research. So in the biodiesel research, we usually obtain the lipid, and the other macromolecules like carbohydrates or proteins are usually wasted. So in order to use these chemicals, we try to collect it and try to process it into a useful product such as bioadhesive. So we collect the protein and denaturize, and likewise put some cross linkers to create a bioadhesive product. So this bioadhesive is like a wood glue, or a typical glue that is used in plywood manufacturing, and likewise some furniture related works. In case of the nanocrystalline cellulose, so basically this is also a continuation of the project that we had before about the nanocellulose production from agricultural residues such as bagasse. So here we try to functionalize this nanocellulose in order to remove heavy metals in wastewater. So aside from the absorbent property of this nanomaterial, the other problem is its collection after application in real wastewater. So in order to collect it easily, we try to incorporate a magnetic component like an iron in order for us to easily collect it after the adsorption process. As you can see here, we tested it in a copper solution, and after the whole process, we collect it using a magnet. So in this way, the collection of the magnetic nanosorbent can be easily done and use it again later. Okay, and for the work of Engineer Mulimbayan, so I think they are trying to investigate the property of stainless steel, especially its corrosive property. So as we all know, stainless steel is usually used in food processing or food packaging. So what they're trying to do is to investigate. By the way, there's two type of stainless steel, the SS300 and the SS200. I think the SS300 is the commonly used, but this type of stainless steel is usually expensive. So we are dealing with the SS200 in order to, this is cheaper compared to the SS300. So by determining the corrosive property of this stainless steel, later on, maybe it could pave a way into its further improvement. And by analyzing the corrosive property, maybe it can tell us how to improve further the property of the stainless steel, especially in food application. The other one is the investigation of anode material for solid oxide electrolysis cells. So this is an electrolytic um, cell that is used to produce an energy, especially the hydrogen. So the group of engineer Baso is trying to produce a high conductive material with the incorporation of strontium dope lanthanum manganite and yttria dope zirconia compound. So electrolysis, what we all know about electrolysis process is that it usually consumes a higher energy than the amount of energy that is being produced. So in order to have an efficient electrolytic process, I think we need to have some specialized material, especially with the high conductivity that can make the whole electrolytic process eh, uh, uh, um, can consume a lower energy compared to the typical electrolytic process of splitting hydrogen and oxygen in water. So let's move on with our research on the polyhydroxyalkanoate. So actually this research started in 2017. So this is a grant from the Fisher DOST. So before I will go with our accomplishment, I will discuss first some of the concepts behind this project. So let us define first what is a biorefinery. So biorefinery is a sustainable processing of biomass into a different bio-based products and bioenergy. So by the way, this is almost similar to a petroleum refinery, except for the use of renewable feedstocks, so such as the agricultural residues. So it is a concept of converting biomass um, into biofuels such as bioethanol, biomethane, and biodiesel, and some bio-based chemicals such as acids. And likewise, in terms of heat and power, it can also be used to produce. And this is a potential solution to replace the petroleum refineries and to reduce the footprint that we have on the use of fossil fuels. So this is a typical oil refinery example. So as can be seen in these slides, there's a lot of chemicals that can be derived from oil refinery. But checking on the finished products and consumer goods derived from it, it shares similar end market with the biorefinery process. So this is the flow chart of the biorefinery example. So here we have the biomass feedstocks. So from these macromolecules, starch, cellulose, lignin, and oil, so we can produce sugars from them, and likewise bio-based gas. And after the sugars, we will create some building blocks. So, and some secondary chemicals and intermediates. In the end, the commercial use of the derived products is commonly found in the industry. So such as and additives, control chemicals, transportation such as fuels, and likewise polymers like plastic materials, textiles, etc. So there's two major approaches in biorefinery system. So the first one is the biochemical approach, and the other one is the thermochemical approach. So I will deal mostly with the biochemical approach, since this is my this is my area of research. So in the biorefinery system using the biochemical approach, usually we have this raw feedstock. So we can classify them as first and up to fourth generation feedstock. So first generation feedstock is commonly obtained from sugar, starch, or oil seed crops. The second generation are usually from wood, grassy, or agroforestry residues. So these are waste generated from the first, usually generated from the first generation feedstock. So basically, first generation are human food commodities, where in this report, I will be concentrating more on the second generation feedstock. So there's also the third generation, which is the algal feedstock, and the fourth generation, which is some sort of industrial waste. So comparing the first and second, the second generation or ligno cellulosic conversion process is quite more complex than the first generation. So for the second generation feedstocks, it undergoes several bioprocessing to extract the carbohydrates, proteins, or lignin from it. So usually we need to have some pretreatment in order for us to break the primary protective layer of the plant, which is the lignin, and partial degradation of the cellulose material. For the pretreatment process, there's a lot of pretreatment method that can be used, ranging from mechanical to thermochemical. So it was already extensively studied, and based from these studies, the steam explosion was selected to have the highest potential among other pretreatment. So as can be seen in this table, it has the highest TRL, or technology readiness level, and have several success stories at pilot scale level. So due to the added steps, the lignocellulosic biorefinery platform has a lot of challenges. However, its drivers and opportunities, like environmental challenges, food versus fuel dilemma, wide range of potential bioproducts, and bioenergy applications, may somehow outweigh these challenges. So the ligno biorefinery have a lot of commercial products that can be derived. So again, from the cellulose to lignin to glycerol that can be extracted, it can be bioconverted using some fermentation or chemical conversion process to produce these alcohols or acids, and likewise PHAs. So lignin and glycerol also has value-added product from this lignocellulosic biomass. So in US, the US DOE have this or identified some of the major platform chemicals in year 2005. So as can be seen, mostly acids products, sugar, alcohol, glycerol, and sundiols are among these major platform chemicals from a biorefinery system. So it is no wonder why they are selected, since these products are referred to us as a primary product, meaning they are easily produced aside from their high market demand. So similarly in Europe, so in year 2015, they also identified some essential platform chemicals. So these are, I think, 25 platform chemicals. And likewise, they categorize it based on this and their technology readiness levels, meaning this level is a gauge where the production of these products is still an infancy to pilot or demonstration, or even commercial scale processing. So based from this figure, I think PHA production is still on the demonstration scale, but some companies are already producing it into a commercial scale production. So again, these 25 chemicals are categorized as alcohols. So one of this is the ethanol, and some organic acids, and likewise polymers. So again, PLA and PHA share a lot from this polymer production of this biorefinery system. In this table, I'm a little bit struck because it represents a lot. So for example, here acetic acid and likewise ethanol, their price is, I think it's a little bit low compared to the other product listed here. And likewise, in terms of PHA, I think it is one of the most high valued chemicals in terms of in terms of bioconversion process. And again, these products are assumed to have no share from the conventional fossil fuel derived products. So again, it entails that PHAs can only be produced using the biochemical route. So let's discuss more about the PHA production from agricultural residues in the Philippines. So again, let's check the current status of PHA production in our country. But before that, let me introduce to you something about the background of this study. So again, PHA, maybe it's not common to us, but basically PHA is a type of bioplastic, a true biodegradable plastic. So unlike some of the commercial bioplastic that is introduced in the market, PHA is the only bioplastic that I know that is truly biodegradable. Truly biodegradable. So again, this research is being made because of this some studies that we have. So by year 2048, it was stated that there will be a global collapse, or there will be a time where when our ocean will be no more fishes or marine animals because of human exploitation, habitat destruction, or climate change. And likewise, based on the figure, the center of this at the center of this slide, so I think it's not easy to distinguish which one is plastic bag and which one is jellyfish, right? Okay. And again, plastics has become one of the basic human commodities because of its versatile qualities of strength, lightness, and durability. However, it made it one of the recalcitrant pollutants in the environment. Hence, I think it would not be it's an exaggeration to say that plastics constitutes around 90% of all the trash floating in the world's oceans. And I think maybe this is not already new to us. So among the plastic offenders, the Philippines is the third country that is, I think, producing a lot of plastic waste. So next to Indonesia and China. I don't know if this is true. I think this is somewhat maybe we are not the producers. Maybe baka napunta lang sa mga dagat natin yung mga plastics na to. So that's why because we are an archipelago. So commonly used plastic polymers. So again, they are categorized into PET, HDPE, LDPE, and they are usually found in our soft drink containers, rigid containers, package films, and likewise polystyrenes in our foams, and polycarbonate in our baby bottles, sport water bottles. So most of these plastics are produced using the conventional or using fossil fuels. So these are plastics that can be recycled. However, they are not economically feasible to recycle. So mahirap siyang i-recycle. So the problem with conventional plastics, so they produce dioxins when burned. And again, recycling is very uneconomical and labor intensive. It causes some skin and respiratory related diseases. And this is a common problem. So it usually contaminates our ecosystem. It doesn't undergo microbial degradation. It can seep through our groundwater. And likewise, it takes a lot of years to degrade. And again, the rising issues today is the production of microplastics. So there's some alternative for non-biodegradable plastics. So they are categorized as chemically synthesized polymer. So example of this are the polyvinyl alcohol, polyethylene, polyglycolic acid, and likewise starch base, or the starch polyethylene composite. And the other one is PHA, which is something new to us. Okay, so among these biodegradable plastics, I think PHA is the only one that is 100% biodegradable. For the starch base, it is biodegradable, but the remaining plastics, which is the polyethylene, so usually kinocombine yung polyethylene and starch. So the remaining polyethylene is not biodegradable. Only the starch is the biodegradable material in our starch-based bioplastics. And likewise for the chemically synthesized polymer, it is susceptible to enzymic or microbial attack, but again, it is dependent on the condition or the environment that this material are being put into. And this is also not considered as commercially viable substitute for plastics. Going back to PHA is 100% biodegradable, and likewise, the properties of PHA is almost completely similar or somehow more excellent than with the synthetic plastics. let's move on with the oxo-biodegradable plastics. So these are the plastics that we found in supermarkets. So ito yung mga typical na bag na nakikita natin na oxo-biodegradable plastics. So don't be fooled with this type of propaganda that they said that oxo-biodegradable is really a biodegradable plastics. So it is not. So oxo-biodegradable plastics is a type of conventional plastic film that is incorporated with metals. So nangyayari po dito is upon exposure to UV light, so there's a cracking in the material, and somehow the formation of tiny particles somehow parang nakikita natin na nagde-degrade siya, but in reality it is just being formed into tiny particles, or these plastics just became it microplastics, so it doesn't degrade. So the fossil fuel based plastics here like PE is still in our environment, but due to the tiny or naging maliit na siya, that's how parang sinasabi natin na nag-degrade siya, but actually they just turned into a microplastic which is still inert and recalcitrant in nature. So this is one of the study made, I think just in year 2019. So they tried to study the different biodegradable plastics in our commercial stores, and they found out that after exposure to harsh condition like in sea, in soil, and open air over a 3 period, so the biodegradable plastics that is being used is still actually we can still use after the 3-year period of exposure in our environment. So they are not really biodegradable as being claimed by these producers of this bioplastics. So again, these are the categorization of the bio-based plastics. So it could be renewable and biodegradable, renewable and non-biodegradable, and biodegradable and combination with petrochemicals as raw materials. So it's only the PLA, PHA, and some starch blends, as what I said in the previous slides, that are truly or somehow near degradable and likewise renewable materials. So for PHA, among the biopolymer, it was cited that PHA and likewise PLA are the main drivers of the growth in the field of bio-based and biodegradable plastics. So based from this figure, it could be seen that PHA has the relative increase in 2021. So this year, along with other bio-based products such as PET and PEF. Okay, so for polyhydroxyalkanoates, so they are accumulated inside a microbial cells as carbon and energy source. So they are usually produced under low limiting nutrients and excess carbon. So there are two types of PHA, the short chain length, so depending on the number of carbon chain, and likewise we have the medium chain length, which is typical ranging from 6 to 14 carbons. So in our environment, there are 300 different bacteria that can be that can produce PHA. So they are categorized as gram-positive or gram-negative. So for the property of PHA, it is water insoluble. So it doesn't degrade when exposed to water. And likewise, it has a good ultraviolet resistance. I think this is a property that's good in food packaging and some other application. It is soluble in chloroform and other chlorinated hydrocarbon, biocompatible. So this is a fascinating property that can be used especially in advanced applications such as in medical or pharmaceutical fields. So it sinks in water, so it doesn't float, so meaning when it sinks, so I think it will facilitate faster degradation because napupunta siya sa ilalim ng let's say rivers natin or yung dagat natin. So there's more microbial activity beneath the surface of our water system. Okay, so non-toxic and less sticky than traditional polymers. So I think this is something to do with the processing later on of this material. And the properties may be manipulated by blending polymers or and likewise, its property also is could be based from the type of bacteria later that is being used in the production of PHA. So this is the PHA structure. Okay, so again, it could be depending on the substrate type. So PHA can be polymerized into short chain, medium chain, or combination of this short chain and medium chain length PHAs. So this one could give a unique characteristic and has a lot of room for research improvement. So actually PHA is not something new. So it's just re-emerged again this date because of the problem with the plastic production. Okay, so by the way, in 1900, it was already found that it is found in Bacillus megatherium that there's a polymer that is being produced inside the microorganism, and somehow in 1958 it was observed again by the group of Macrae and Wilkinson that when there's an excess glucose and likewise limiting amount of nutrients, there's a PHA or reserve material that is being inside the cell. And in year 1973, I think this is also when we have some problem on oil crisis. So aside from the research on the on the production of biofuels, I think this also the creation of research on bioplastic production is being also widely investigated. And somehow in 1976, the first commercialization of PHA was being introduced in the market. And up to this date, there are some manufacturers that produce PHA on a commercial scale level. Okay, so just to show you the PHA content of the bacteria that is being used in PHA production. So for the gram-negative, the PHA content can be as much up to 90%, so meaning in a single cell, the total amount of PHA or content of PHA in a single cell is around 90%. So basically 10% na lang yung natitira as a functional yung part ng cell na, let's say, yung cell wall ganyan, yun yung natitira na lang dun sa isang cell. So 90% usually constitute of the PHA. So meaning there's a lot of PHA that can be obtained from this bacteria itself. And likewise, the productivity of PHA is somehow high. It's around 5 gram PHA per liter per hour. So this is based from the gram-negative. But for the gram-positive bacteria, it is somewhat lower. But the type of PHA being produced is somehow more has higher quality compared to the gram-negative bacteria. So usually medium chain length yung na create nila, which is better PHA type compared to the gram-negative bacteria PHA production. In terms of the property, so mechanical and other property of the PHA, I think PHA somehow robust, or it has a lot of fascinating properties. So its molecular weight it varies from 10 to 10,000 times 10 to the 4 Dalton. So again, it is something to do with the molecular weight distribution is it is something to do from a typical plastic to a rigid plastic formation. Likewise, each melting point, so it has a very wide range of melting points. So it means it can be easily extruded, molded, or casted into film, etc. And likewise, the elongation, tensile strength. So again, it is varies from 2 to 1,000. So the range is so high, meaning we can manipulate the pH property in such a in order for us to produce or to synthesize this pH property depending on the type of application that we are targeting. Unlike for other plastic material like PLA, PBS, or bacteria plastics, I think the common ranges are somehow narrower compared to the PHA plastics. Again, PHA is really fascinating material for bioplastic synthesis process. As of the moment, the major factor that contributes to the cost of PHA is the cost of the raw materials. As we can see here, it is almost half of the production cost is being put into the type of raw material. So that's why in our research we are dealing with the utilization of agricultural waste or residues, since this is usually cheap, and likewise kung minsan wala pa nga silang buy, so we can exploit it in order for us to produce a PHA product. So currently the PHA production is 2 to 15 US dollars per kilogram. So last time we ordered abroad, and somehow we paid them around 1,000 peso per kilogram of PHA. So these are the companies that produce this PHA. So we commonly found them in China, US, Europe. So these are big companies. In comparison to PET or PP plastics, so usually mababa lang to kasi these are just a byproducts or latak lang ng petrochemical industry process natin. Okay, so these are the accomplishment and current status of our project. So again, medyo marami na rin. So we screened the best PHA producing bacteria, and likewise we assessed and selected the best residues for PHA production, optimized the fermentation conditions, and likewise the pretreatment and hydrolysis process. And again, we produce PHA from actual hydrolysis. Hydrolysis is the process biomass. So this is a sugar-rich solution. And likewise, we confirm the produced PHA. And up to this date, we are scaling up our PHA production into a pilot scale level. So to give you a background of this raw material selection process, so we have different types of raw material that is being tested. So banana soda stem, pineapple peelings, corn stobber, sugarcane bagasse, and sweet sorghum bagasse. So again, we use MCDA in order for us to lessen our work. So mahirap mag-experiment. So we use some modeling tool in order to select the best substrate for this production process. So we have some criteria for this selection process, and we found out that corn stobber is the excellent feedstock candidate. And again, based from its conversion efficiency, processing costs, and I think composition also. So next is banana pseudostem and sugarcane bagasse. And likewise for our strain, so Bacillus megatherium, so this is our very own strain. So it is a strain that is being isolated by UPLB Biotech. So this is a wild type, and there's a room for improvement later, especially for its genetic engineering. And likewise, typical problem in biochemical conversion pathway is the consumption of the monomeric sugar. So usually only glucose or the C6 carbon sugar is being consumed. But in this type of strain, it can both consume glucose and xylose. Likewise, we found that this strain can produce PHA at a shorter period, and likewise, it doesn't necessitate a high glucose concentration during fermentation. So for the confirmation of the PHA product, so we have this extracted PHA, so para lang siyang film, and actually it undergoes some extraction process and likewise purification process using solvent. Okay, and we compared it with the FTIR diagram of the PHA standard, spectra of a PHB standard, and our crude PHA, and it shares similar spectrum with the standard. So again, we confirm that we really produce this PHA material in our process. Likewise, we are investigating also the blending of PHA with other natural fillers or other chemicals. So we tried cellulose, likewise starch and calcium carbonate at different ratios using the solution casting method. So somehow we improve further the property. So I did not show here, but actually it doesn't degrade the PHA property. And likewise during biodegradation tests, so the same. So usually nangyari kasi if we incorporate other material with the PHA, it doesn't biodegrade after. But what happened here is that it degrades in a certain environment. So this is a compost conditions, meaning medyo enhance yung or facilitated yung degradation process niya. So after 2 weeks, after incorporation into a soil compost, so after 15 days, I think we didn't found any more films in this soil conditions. So really, the biodegradation of the material is happening, or hindi siya nandun pa rin sa environment. So it really biodegrades. And likewise in terms of its applications, so we are also investigating its application in 3D printing. Somehow mas madali kasing maggawa ng prototype using a 3D printer. So here we are trying to come up with a filament. Okay, so the most common filament used in 3D printing is the PLA base or the polylactic acid filament. So PHA is not new in the market, so we are trying to produce a PHA-based filament because for a PLA there's a lot of problems. So usually during printing, madali siyang mag-distort or mag-warp, and somehow if this bioplastic is being exposed under the sun, nalulusaw siya. So we are trying to have a more tough or less brittle filament, which is yun nga yung PHB, which is PHB is a good material. So far we tried a composite material, PHB filament production using filament extruder. So I think we create filament and somehow medyo okay naman siya, and later on we will try this filament in a 3D printer. Okay, for the scaled up PHA production process, so we collected several biomass. So actually ito yung nasa harapan ng IRI. So left side nung pili drive natin. So we collected the corn stobbers. As I said earlier, corn stobber is the top substrate for this PHA production process. So we collected ito isang jeep, okay, nung corn stobber biomass. And likewise, we process it. So there's a lot of processing. So we need to dry. So sun drying first, then again further remove the moisture of this material oven drying, and again shred to have tiny particles, and likewise summer milling. So the final milling process is the production of a powdered particle through the cutting milling process. So this powdered biomass is being forwarded to a third-party hydrolysis productions because we don't have much larger equipment to produce this amount of hydrolysis for the upscale PHA production. So we hired a third-party hydrolysis provider abroad. So ito yung Institute of Nuclear Energy Research in Taiwan. So we managed to forward or send 50 kilogram of corn stobber biomass. So they process it using their own steam explosion reactor, saccharification and reactor, and try to concentrate, sterilize, and pack before shipping to us again. And here is the final product, yung hydrolysate or processed biomass, which is the hydrolysate product. So today we are investigating the hydrolyzate produced abroad, and later on we will try to optimize the whole process in a 5-liter bioreactor, and finally fine-tune or validate the PHA production in a larger scale bioreactor or fermenter. So this is the whole picture of the PHA production process that we are doing. So again, collection of biomass. So we have this powdered corn stover. It undergoes pretreatment, hydrolysis, sterilization, and fermentation. And after that, we will collect the cell and extract the PHA from it. So from the flowchart of this diagram, so we initially calculated that from a 30 kilogram powdered corn stover, the amount of PHA that can be extracted is around 1 to 3 kilogram PHA. So I think this is not bad considering that we have this cheap material from it. Okay, so for the technology or project roadmap of the project, so actually the project will end this June, and we hope that we can do some market and feasibility studies after the upscale processing. And somehow, hopefully we can have another funding for the project for the technology upscaling, PHA product development, strain and process improvement, and likewise investigation of the other type of PHA, which is the medium chain length PHA. So there's a lot of application of PHA. So not only a substitute to our common plastics like plastic bags, but also there's a fascinating area of PHA that we need to study further, like in the field of biomedical or pharmaceutical research field. Okay. So again, we hope that we can still further explore these different areas of PHA research in the future. Okay, so that's about PHA, and somehow we have another big project under the leadership of Professor Reaño. So this is the development of aptamer-based colorimetric and electrochemical point of care type diagnostic test for TB and latent TB infection. So actually this work is on the development of aptamer-based biosensor for tuberculosis detection. So TB is what we always say contagious disease, hence its early detection would limit its transmission. So the point of care detection kit that would be developed by Dr. Reaña's team would be a pioneering research in our country. So we are glad that Dr. Reaña is doing this type of work for an easy detection of tuberculosis in our country or in the whole world later. Okay, so everyone is very eager to see the result of the study. So this is currently funded by the PCHRD. And likewise, we have another project on the biohydrogen production. So by the way, this is the we have a phase two or we obtained additional funding for the phase two of this NRCP funded project. So actually, we in phase one of the project, so we isolated several PNSB or the purple non-sulfur bacteria for biohydrogen production around around Laguna or Los Baños, Laguna. So for the second phase of the project, so we are trying to improve further this PNBs, this chosen PNSB microorganism for the hydrogen production using some optimization, physiological condition optimization, chemical supplementation, some bioreactor designs, and likewise strain improvement. So NRCP gave us some budget for the second phase of the project. For our future research, so the department is a consortia of different engineering fields with different background in materials research. So we are hoping that we can extend our previously started research and explore the other research areas in the field of advanced ceramics, polymers, metals, nanomaterials, biosensors, rubbers, composites, and likewise in food food drying and storage materials. So this from the grants that we obtained, so we are gradually establishing our laboratories. So recently we have established the BE or the Biomaterials and Environmental Engineering Laboratory, and likewise the Materials Engineering Laboratory. So these are laboratories equipped with facilities ready for research and instruction. So we hope that our college and the university will fully support not only our research endeavors, but also our pursuit in the establishment of a BS Mati program of the department. So there's lots of potential of the department that is just waiting ahead or in the corner. So we're very eager to have our very own degree granting unit. So I think yun lang po. So special thanks to our research team, the PHA project. So we have collaborators from UPLB Biotech, from the Department of Chemical Engineering, and likewise we have here Engineer Rick Piso and Tito Louis as our URA and laboratory technician. For the NASA and NRCP projects, so these are, again, we have also collaboration in IBS and likewise UPLB Biotech. So here, our URA, the University Research Associates are Engineer Adorna Rojas and Miss Kerubin. To our hardworking students, our collaborators, co-implementing agencies, funding agencies, and likewise to those I forgot to mention. So maraming salamat po. So we are open for a fruitful collaborations in the future. Okay, so that's it. So thank you very much.
Thank you so much, Doc JR. Thank you for sharing the research accomplishments and the ongoing projects from the Department of Engineering Science. Ayan. So with those researches, no, it's a testament that the department is in shape for the BS Materials Engineering program. And I'd also like to commend Doc JR and all the researchers from the Department of Engineering Science kasi in spite of the teaching load that they are still able to do research and really contribute to the research efforts and the research community of UPLB, actually not just in UPLB. And because of the research projects of Doc JR, dumadami ang equipment sa aming lab at lumalaki din. Ayun. So thank you, Doc JR. Let's give him a virtual clap. and okay, so now let's go to the open forum. Ayan. So Doc JR, I've received questions a while ago, and I'll just be grouping the questions into two. So for the first one, why did you choose to conduct the research on PHA and biohydrogen production? And what is the next direction of your PHA research?
Okay, so I will answer first your initial question. So actually, I chose the research on PHA and biohydrogen production because they are considered basic commodities in our daily life. So, and likewise from an environmental engineering background, so there's a need to produce or to find an alternative to plastic and conventional fuel use. So one of which is the PHA for the bioplastics and the fuel for BH2. So I forgot to mention that in the near future, the current fuel that we are using is being gradually replaced by battery and somehow this hydrogen. So hydrogen, if used, is not it doesn't produce toxic gases. So it only upon combustion, it only produces water and some oxygen. Okay, so unlike conventional fossil fuels, it produce carbon dioxide. So they are environmentally friendly and somehow non-destructive alternatives. So moreover, our research utilizes agricultural residues or some organic waste converted into a high value biochemical platform, which is yung PHA and and hydrogen. So our country is an agricultural country, and the bioconversion of waste product in agriculture lands would be an added income to the farmer aside from protecting our environment. So that is the main gist of the research. For the next question, so actually there's a lot of direction, especially the PhD research. So again, we have this proof of concept that we can really produce PHA. Actually, that 10% production is maybe for if we compared it from the 30 kilogram and we can produce 1 to 3 kilogram PHA production. That is small, but in reality, that is already big. So again, we need to further produce an economically feasible PHA production, like further improvement on the upstream, the pretreatment and hydrolysis process. Likewise, there should be investigation on the other type of PHA, like the medium chain length and somehow strain improvement. And similarly with the PHA extraction process, so we are dealing with the solvent extraction. So it should be more or non-invasive extraction procedure where chemicals is not being used. And also the fermentation process optimization. So marami pang gagawin dun sa fermentation process, like from fed batch to continuous process operation, and material engineering research for the PHA property improvement. So there's a need to incorporate other blending materials, reinforcement, or some chemical functionalization. And finally, the target application of the PHA product. So we cannot just use it as a substitute for typical plastic bags. So I think there should be a higher value application of it, especially in the pharmaceutical and medical fields. So I think what is fascinating in PHA is that it's all about its biocompatibility. So I think somehow we can use it later in drug delivery and likewise sa vaccine. So ngayon kasi ang nangyayari dun sa vaccine natin, we're using a nano lipid coating. So there's a research undergoing, not yet applied, but PHA is somehow a good candidate as a pang-coat dun sa vaccine natin. So yung nangyayari kasi it reduces the degradation of the vaccine pag na-coat siya. And somehow since this PHA material is biocompatible, I think it doesn't have adverse reaction if incorporated or na-introduce siya sa katawan natin. Those are promising research direction of this study, and hopefully we could top it in the future, or we have another funding for it. So we're hoping for this this direction, looking for these directions.
Thanks, Doc JR. Meron lang pong pahabol na question. Okay lang po, sir.
Okay.
In your opinion, what would be done to further improve the research endeavor of the DES?
Okay, so that would be a good question. So actually, the Department of Engineering Science is doing an excellent job by sending some of the faculty pursuing their graduate studies. But so from these studies, so they generate a lot of publication, and likewise they gain some new knowledge. But after this, the conducting the studies, after returning to the department, somehow na-stuck, right? So actually, bumabalik ulit dun sa teaching. So for me, the major hindrance to this research endeavor of the department is the lack of a degree granting capacity of the departments. In reality, we don't have that much manpower. So our ability to conduct research is being hampered. So no time to conduct research, not only because of the heavy teaching load, but also to the lack of students in order for us to help or aid in carrying our research. So usually hindi na natin na-apply yung natutunan natin after our graduate studies. So as I said, the DS has a lot of potential, and actually I'm very proud that the faculty of the DES is still there. So andyan pa rin, and likewise we're looking forward to the establishment of our own department. So we have a very good group. So we have a very good consortium of engineering, different engineering fields that can create and collaborate easily if actually if we need to have to produce a something good research in the future. So I think we are just lucky that we have grants, so DOST grants. So actually we obtained millions of pesos. So as of now, we need to strengthen our ties, not only in CEAT, but with other colleges or institute department, and maybe in some UP units, other universities, and likewise other agencies. So these are the initiatives that we need to establish as of this moment. Aside from the waiting, aside from waiting our yun nga, yung pagka-establish ng BS materials sa program natin later on. So we are hoping for it, and hopefully makita ito ng college, and likewise the need the unit makita ito ng college, and likewise the university, the need that our department is really very eager to have its own degree granting unit. Okay, so yun lang po.
Thank you so much, Dr. JR. What you've said is really inspiring for us. Ayan. So, we're not finished yet. So, we now move on to the second presentation. Ayan. Yes, we have our recorded presentation from the COET team of the Department of Civil Engineering. The COWET team is composed of Engineer Alvin Joseph Dolores, Engineer Victor Micael de Padua, Engineer Maria Hazel Castillo, and Engineer Donny Ray Camis. Do you know that the COWET team from the Department of Civil Engineering was one of the finalists in the OML Center's first Climate Resilience Challenge that intends to address water scarcity while also treating wastewater for the agricultural sector using constructed wetlands. Without further ado, let's watch and hear the recorded research presentation of the COET team. Sorry, Engineer Camus, not Camus. Thank you. You can now play the recorded presentation.
Good day, everyone. I am Engineer Hazel Castillo, and on behalf of the COET team, I would like to thank you for joining us today and for allowing us to share with you our solution entitled COET, a nature-based solution to water security. In this presentation, our team is going to discuss how constructed wetlands can be used to address water pollution and scarcity in the face of climate change. Our solution, specifically a hybrid subsurface flow constructed wetland, is a collaborative research effort between Engineer Camus, Engineer De Padua, yours truly, Engineer Dolores, and undergraduate students of the Department of Civil Engineering, CEAT UPLB. I would also like to acknowledge Assistant Professor Perly Velasco for establishing the constructed wetlands researches in UPLB back in 2015. So currently, Our studies make use of a laboratory scale setup wherein we test different setup configuration, vegetation, and filter media on several types of wastewater. As an overview, our system has the following advantages. So relative to conventional wastewater treatment facilities, COET is considered a low-cost technology. So our system does not require pumps since the flow of wastewater within the system is by gravity. Our system also makes use of reusable materials. So filter media like sand and gravel can be cleaned and reused. Vegetation can also be reproduced, and once the vegetation has actually reached the end of its lifespan, it can be turned into compost together with the removed sludge from the system. So from these mentioned advantages and the ability to recycle treated wastewater, we can see that instead of the make, use, and dispose process of linear economy, constructed wetlands promote sustainability and circularity. And before we proceed with the details of our solution, I would just like to give a brief background on why we started COET. Water can be considered as one of the most used resources on Earth. And like carbon footprint, we also have what is known as water footprint. So water footprint is defined as the total volume of fresh water that is used to produce commodities and services we consume every day. So as an example, it takes about 4,650 liters of water in order to produce just a 300 grams of beef steak. So imagine how much water is used to produce all the food that we eat each day. And not only that, everything that we use, buy, or even wear needs water to be made. Most or some may believe that clean water is unlimited. However, only 3% of the world's water is fresh water. In fact, in 2015, the World Economic Forum has ranked water security as the #1 global risk. Our freshwater systems are increasingly at risk, and the weather patterns are also continuously changing and becoming more extreme. Rivers are drying up, drought or flood are becoming more common. We have stronger typhoons, ice caps are also melting, and global surface temperature is increasing. So you might wonder why such events are happening. These events happen primarily because of climate change. And since climate change is a global phenomenon, the Philippines is also affected by this problem. So some of the climate-induced challenges that developing countries, so like ours, experience include water scarcity and water pollution. And in relation to these two challenges, let us take a look at the wastewater management in the Philippines. Based on studies of UNICEF, only 10% of wastewater in the Philippines is treated. And also, poor sanitation can lead to annual economic losses of more than 78 billion pesos annually. So as for wastewater contributors, based from the 2006 to 2013 National Water Quality Status Report of EMB, the major sources of pollution come from agricultural sector, followed by domestic and industrial. And with the agricultural sector being one of the top contributors of wastewater in the Philippines, agricultural wastewater treatment is needed. However, small-time farmers cannot afford conventional wastewater treatment facilities. Thus, to address these pressing issues on sanitation, water pollution, and water scarcity, we need an alternative source of water and affordable wastewater treatment technology.
So good morning, everyone. So I'm Engineer Victor Michael N. De Padua, and I'm here to discuss more details about the COET system. So as mentioned by my colleague earlier, we developed this to tackle two major problems, which is one, water scarcity, and the next is water pollution. So how do we go about doing that? So we want to treat wastewater for it to be clean enough to be used for irrigation or other non-potable needs. So we are currently targeting the agricultural sector, where we aim to make an alternative water source through the wastewater produced by these farms. So now let's get into detail about what COET is all about. So first, let's discuss the materials. So one of the most important materials and what sets us apart from other conventional wastewater treatment facilities is that we use vegetation. So vegetation is good for nutrient absorption. So the vegetation's root system also holds the filter media in place. And the root system also houses helpful bacteria. So next up is the substrate. So this is the artificial representation of the soil. So usually we use sand and gravel, and we engineer this part such that optimum wastewater flow rate is achieved. So now let's move on to the microorganisms or the good bacteria that I was talking about. So it's responsible for biological processes that degrade organic pollutants. So nitrification for aerobic areas and denitrification for anaerobic areas. So basically, these two processes complete the nitrogen cycle, which break down ammonia, which is a pollutant, down to nitrogen gas. So originally, it's housed in the vegetation's root system, which extends to gravel because of its large surface area. So next we have the tanks. So these are the containers that we use to separate each individual phase of the co-wet system. So we have the sedimentation tank, the vertical flow tank, and the horizontal flow tank. So these tank dimensions are calculated to ensure proper flow of wastewater. And finally, we have the part that connects all these systems, which is our pipe system. So in our lab setup, we use PVC pipes and valves to regulate the flow of wastewater throughout the system. So as you can see from the image, so the pipes are perforated such that the spread of wastewater is even throughout the system. So to your left is a picture of our lab scale setup, and to the right is a cross-sectional view of the system. So I'll briefly discuss the journey of the wastewater from the settling tank to the outlet pipe to show you how the system works. So the wastewater's journey through the co-wet system begins at the sedimentation tank or the settling tank. So we use it for overnight sedimentation, where the heavier particles in the wastewater eventually settle to the bottom. So this is what we call sludge, and when we extract it through the sludge outlet, it can be combined with dried vegetation from the system to create compost or fertilizer. So after the sedimentation tank, the wastewater is transferred to the vertical subsurface flow tank. So since the flow rate is fast, the filter media is never saturated. So there's always pockets of air or oxygen. Because of this, nitrification takes place. After the vertical subsurface flow tank, we proceed to the horizontal subsurface flow tank. So at this stage, the flow rate of the wastewater is much, much slower, which leads to saturation. So since there are no air pockets, the environment is anaerobic, where the nitrification takes place. The combination of the vertical and horizontal flow systems complete the nitrogen cycle. So in the vertical tank, so the ammonia is broken down by the bacteria into nitrites and then into nitrates. And in the horizontal tank, where the nitrate is further broken down to the harmless nitrogen gas, which is released to the atmosphere. So after the wastewater passes through the whole co-wet system, what we get is treated wastewater that's clean enough to be safely released to the environment. Or with the additional step of chlorination, we will be able to use the treated wastewater as an alternative water source for non-potable needs. So by no means is constructed wetlands a new technology. What our team is doing is we are implementing and adjusting that technology to fit the Philippine setting. We are using low-cost materials, and the design is highly scalable, such that small-time farmers to big companies should be able to create their own co-wet systems to fit their needs.
To put COVID to the test, undergraduate thesis students of the Civil Engineering Department of UPLB conducted an experiment to determine wastewater treatment efficiency of COVID on UPLB swine farm effluent. The swine farm in consideration houses 593 heads of pigs that discharges 27,360 liters of wastewater from their daily operations. The experiment lasted for 21 days. Daily operations by removal and application of wastewater all throughout the period. Treated wastewater samples were collected on days 1, 8, 14, and 21. Samples were sent to Austria Mineral Laboratories in Binyan, Laguna for water quality analysis. The study used stem cuttings of hybrid napier grass, essential Florida, as vegetation for this experiment.
Excuse me, naririnig po ba? Okay, what? I'm so sorry.
Yes, sir, we can hear.
Wala po, sir.
No sound, okay. Na-disconnect yata. Thank you. Okay, I'll go back, okay? Which part? I think this one, okay?
Farm effluent.
Kita na po ba?
The swine farm in consideration houses
Yes, sir.
593
Okay,
heads of
thank you.
pigs that discharges 27,360 liters of wastewater from their daily operations. The experiment lasted for 21 days with daily operations by removal and application of wastewater all throughout the period. Treated wastewater samples were collected on days 1, 8, 14, and 21. Samples were sent to Austria Mineral Laboratories in Binyan, Laguna for water quality analysis. The study used stem cuttings of hybrid napier grass, Essentia Florida, as vegetation for this experiment. This plant species is very abundant in the UPLB campus near the Dairy Training Research Institute, and it is somehow considered as a weed. Likewise, according to Gurahu in 2005, hybrid napier grass is very effective in the removal and absorption of nutrient from wastewater. Different parameters were observed in the experiment. Among them was turbidity, which shows great difference between the effluent and effluent qualities after running through the system. Nutrient contaminants observed were total nitrogen and total phosphorus. Originally, it shows good removal efficiency until days 14 and 21. From the graph, we can see poorer removal efficiencies, which were attributed to the plant death at beds in day 14 and day 21. Good thing is that for the biological oxygen demand and the total suspended solids, the removal efficiencies were high enough to have the effluent pass the DNR Administrative Order 2016-08 and the Department of Agriculture Administrative Order 2007, which dictates whether effluent can be discharged or can be reused. For the biological contaminants, total coliform and fecal coliform were observed, to which both contaminants removal efficiency were observed at a very high rate of more than 99%. Sadly, since the influent has a very high concentration of biological contaminant, still the effluent did not pass the DNR and the Department of Agriculture standards. Considering all the factors and all the results of the study, here is a sample of the proposed full-scale constructed wetland treatment facility that includes a disinfection tank to address the total and the fecal coliform removal. The facility covers an area of 88 square meters for the population of pigs housed in the facility. But what's most important in this specific study is that how do the stakeholders think about this specific project? In the article titled Perception-Based Social Acceptability of Subsurface Flow Constructed Wetland Treated Dairy Farm Wastewater Reused for Irrigation by Camus in 2020, the objective of the specific study is to determine the social acceptability of using co-treated wastewater for irrigation of crops. The study sent treated wastewater samples to local farmers in Laguna with varying crops to determine whether they would want to reuse it or not. The survey was specifically designed to gauge the knowledge of the respondent on how the wastewater affects their environment, how it should be managed, what are the existing laws, and what are the possible reuse of the wastewater. Socioeconomic profile, as it is one of the main factors in considering the analysis, was also gathered for the specific study. The results show that the respondents are very aware of the adverse effects of untreated wastewater when discharged to the adjacent environments like rivers and different bodies of water. High level of willingness to pay or to be taxed was observed for the COET to be implemented. Majority thinks also that the government has the main responsibility in treating the wastewater before it is discharged. Surprisingly, the second majority believes it should be a collaborative effort between the government and the stakeholders. The respondents are willing to use the reclaimed wastewater for irrigation. This specific study of Camus in 2020 shows high social acceptability of the use of COET in terms of wastewater treatment from dairy farm and swine farms. For this specific result, we can conclude that COET is a promising technology in addressing water scarcity and water pollution in the near future.
Constructed wetlands can be considered as a climate resilient technology. Aside from wastewater treatment, it can also serve as a medium for creating new habitats, for controlling floods, and for reducing temperature in urban areas. It can also provide green spaces, which can improve the overall look of our local communities as well as provide sites for recreational benefits. Lastly, it addresses water scarcity by enabling non-potable water reuse. For example, for irrigation or for toilet flushing demand. Moreover, constructed wetlands takes advantage of the circular economy as opposed to the make, use, and dispose model of the linear economy. So, in the circular economy, once we use a certain commodity, we can either treat that commodity for reuse or use its byproducts for another purpose. For example, vegetation which grows within the constructed wetlands can be used as fertilizer or additives for the feeds. Moreover, filter media which was previously used for treatment may be cleaned for reuse, while the constructed wetlands can double as a flood mitigating system. Lastly, treated water can be reused or recycled for non-potable needs. Overall, the constructed wetlands technology is a relatively low-cost and sustainable solution that improves water security and access, making it a vital instrument for climate change adaptation. In our group, we envision that in the future, constructed wetlands technology will be used in urban and residential areas, particularly for treating greywater or domestic wastewater. With that, our team intends to do more research on, first, the use of recycled waste materials as substrate or filter media, and second, the effectivity of constructed wetlands as instruments for flood mitigation and carbon sequestration. With that, our team envisions that COET can be a sustainable system to tackle environmental problems. It is a low-impact development that can aid in flood mitigation by delaying the flow of the stormwater within the urban community that it serves. It is a facility that can increase non-potable water supply through treatment and reuse, and it is a green space that can contribute in carbon sequestration, especially in urban areas where we lack green spaces. We hope that COET will be a remarkable addition to the wave of green infrastructure interventions happening around the world. Through COET, our team aims to improve the quality of life in all of the Filipino communities as a whole. We would like to end our presentation with a statement from the World Wildlife Organization. We humans, as stewards of the environment, have the capacity and the obligation to mitigate or even eradicate these detrimental effects which we have caused on our environment. We hope that through COET, we will be able to ease these effects of climate change and water scarcity within the country. That ends our presentation for today. Here are references for the presentation. Should you have any inquiries regarding our project, feel free to contact us through the email addresses indicated. Thank you very much for listening, and mabuhay po tayong lahat.
Okay, thank you very much, Department of Civil Engineering, for sharing this research accomplishment by the COET team. Again, thank you, COET team led by Engineer Dolores, Engineer De Padua, Engineer Castillo, and Engineer Camus. And by looking at the application and the technology, we can see that it will really benefit many farmers. Ayan. So now we move on to the question and answer. And I believe we have here Engineer Castillo, Engineer Dolores, and Engineer Camus for the open forum. And so I only received 2 questions. Okay, so for the first one, okay, if the COET system will be scaled up, by how much are the farmers willing to pay for the disposal and treatment of wastewater using this technology? And which institution shall oversee the implementation of COET in your target areas? Is it the national government, the LGU, private sector?
Hello, good morning, everyone. So, thank you for that question. No? It's typically with the culture of the Philippines, we don't usually reuse, di ba, yung wastewater. Especially we know na galing yan sa isang swine farm or sa isang dairy farm. No? Alam natin na yung ihe and then yung dumi ng animals. Yung ano. So, it's quite interesting to see that based on our study in 2020 that was published, the farmers which we surveyed gave they are willing to pay at around 12 pesos in 12.625 pesos per cubic meter for the treatment and then the redistribution of the wastewater. So this study also showed na according to the surveyed participants, it is primarily the government's duty to do the treatment and then redistribute it. But it's like what we've said from the presentation, it's quite surprising na the second majority believes na it should be a collaborative effort between the government and then the private sectors as well as yung ibang stakeholders like yung mga end users ng byproduct ng system.
Thank you so much, Engineer Camus. And for the second question, how can a COET system be applied or transferred from rural to urban or residential setting?
Should I answer? So, good morning, everyone. So, the idea or concept of constructed wetlands for wastewater treatment of both the rural and urban or residential setting is the same, but we need to recalibrate our design or recalibrate the design of the system since technically the characteristics of agricultural wastewater is totally different from domestic wastewater or gray water, which is common in urban areas. For example, the extremely high coliform count of agricultural wastewater, which we tested, requires the addition of disinfection tank at the end of the system. So this may or may not be needed when it comes to treating gray water or domestic waste since the coliform count is much lower for domestic compared to agricultural waste. So we would also like to develop our research on using other materials for the filter media when we would apply it in urban setting. So for example, since construction materials or the construction debris such as ceramic tiles may be recycled and reused for as filter media for the constructed wetlands. So since these are abundant in domestic or urban settings, we are trying to use this recycled construction debris or ceramic tiles for the filter media. So it is actually one of the next step of our study, and the use of also other types of vegetation which are more suitable for domestic wastewater may also be further researched or explored. So that is actually one of the next stages of our research. So hopefully we can proceed with the study for the application of COET system in the urban or residential setting. So that's it.
Thank you, Engineer Castillo. If others have questions pa, you can also unmute. Unmute yourself.
Hello, good morning. First, thank you very much for accepting our invitation to the COET team. No, so thank you for sharing your studies. Okay. My first question is the target. What I'm thinking is the target of this project is to comply with the DOUT 2016-08, but unfortunately we were not able to reach that one, no? To comply, to meet the standard, especially for total nitrogen. Okay. And I noticed you suggested to add another process, which is disinfection. But I think hindi siya enough para mapababa because nitrogen removal is basically biological treatment. And yun sa chlorination natin or other disinfection processes ay para lang talaga siya sa mga microorganisms. Okay? So ano kaya yung pwedeng alternative or further, kunwari, either post or pre-treatment para mas to lower the concentration of nitrogen. Okay. And then the other one, para tuloy-tuloy na, okay, as Engineer Castillo said, you are suggesting to have other vegetations. Actually, that's my question again. Have you tried other vegetation? Pwede ba itong makain? Para din, you are talking about circular economy, no? So, baka pwede, no? Para meron pa tayong maibenta. Okay, thank you.
So ayun, siguro first question pagdating doon sa nung removal efficiency doon sa nitrogen, sa nitrate at saka doon sa ammonia phase. It was primarily because doon sa setup na ginamit namin for this specific na study ay may mga namatay na mga vegetation. So with the loss of vegetation, konti lang yung magde-degrade or konti lang yung magko-consume ng nitrogen, yung nitrogen-based mga nutrients from the wastewater. But there were yung mga kasunod na studies showed na ng mataas nung nutrients from the wastewater. So kaya with this one, we just decided to add yung chlorination kasi yun na lang talaga yung isang problematic area pagdating doon sa effluent. Plus sagutin ko na rin yung second question was, have we tried yung sa vegetation? For now, we are using yung we use yung hybrid na napier grass primarily kasi kaya namin na-consider na circular economy siya. The napier grass is being used by the farm as feedstock to their as their sa kanilang mga animals doon. So it is one of the major sources ng food din ng talaga. So pwede natin siyang ipakain din sa But for yung sinasabi mo pwede makain, for now, we are planning to use muna yung ornamental plants. At least, hindi kasi siya for direct consumption. Primarily, ang rason ay yun nga kung posibleng contamination pa noong yung fecal coliform at saka yung E. coli dun sa So, but we're moving towards that that path na baka pwede natin magamit in the future. Yun nga lang, we need to expand pa yung aming study. So, tama ba ako, Ms. Hazel?
Yes, sir.
Ayun po. I hope that answers the question, sir.
Thank you very much. Engineer Hazel, do you want to add more?
No, I'm okay po.
Okay. Thank you.
Yeah, thank you so much, Doc RC, for your question, and of course to the COET team for answering all the questions from our audience. And do we still have questions from the audience? Questions? Okay, I think there's none. And so thank you so much, COET team, for sharing this research accomplishment to us and for really making an effort to make a recorded presentation for this celebration. Thank you so much for being part of CEAT's 109th founding anniversary. Ayan. So this is the last part of our program. So I just like to thank all the speakers, Doc J.R. Ventura and the COET team for participating in this, in presenting their research accomplishments for the webinar series today. And I'd also like to thank our host department, the Department of Engineering Science and the Department of Civil Engineering. Thank you so much for all your efforts today and of course for all who attended. Even though it's I think it's the anniversary of EDSA People Power Revolution today. And aside from that, you've became part also of the fourth day of the CEAT webinar series. Ayan. Thank you also to our guests, to our students who attended today. And I'd also like to recognize the presence of our Professor Emeritus, Dr. Movillion. Thank you so much, everyone, for attending. But before we really end this webinar, let's have a photo op. Miss Jane, so kindly open your cameras for us to see your beautiful smiles. Kindly open your cameras and show us your beautiful smile.
Okay, Jane, count ka lang. Jane. Are you okay, Jane?
Okay po.
Okay, go ahead.
Nintay ko lang po lumabas yung camera po.
Okay.
Okay po. Taking pictures in 1, 2, and 3. Next page po. 1, 2, and 3. Thank you po.
Thank you so much.